Yeah, good morning, everyone. It's a great pleasure to welcome you here to the QBN webinar on diamond quantum sensing. And today we would like to take you on a journey from engineering diamond for quantum technologies and the different types of materials over a scanning NV microscope already used today to advance research in material science and spintronics, and to an industrial perspective on diamond quantum sensing. Therefore, we have put together a special program for you with speakers like Mathieu Markham, who is principal research scientist at Element 6, and Mathieu Munsch, who is CEO and co-founder at Qnami, and Rölver, senior project manager at Q.ANT or Q.ANT. So I can say to this topic, I'm really impressed by the technological advancements during the last year. When I wrote my diploma thesis on NV centers, we needed a complete optical table for the setup, which you can buy now from Qnami as a small product. So I'm really impressed by this. I showed one of the pictures from my diploma thesis in another webinar, so I will link it in the YouTube video. Okay, just a few words about the webinar. So the webinar has been recorded. You can watch it on demand on the QBN YouTube channel. You can ask questions if you are on Zoom in the Q&A box. If you are on YouTube, you can use chat or just write us an email on info@quantumbusinessnetwork.de. Yeah, I just want to give you a short introduction about QBN. So my name is Johannes Verst, and I'm quantum physicist, company builder, and CEO of QBN. I founded the International Quantum Business Network to provide the European quantum community supportive structures and develop a strong quantum industry in Europe. From my cluster management background, I knew of the power of innovation clusters, especially in deep tech, and quantum technologies are the deepest of deep tech. And therefore, I found QBN. Why a network? Because a network is more than an ecosystem. In an ecosystem, every person and organization is in charge of their own partnerships, their own business development, their visibility, and so on. And by adding a cluster management to support all stakeholders and manage the collaboration processes within this ecosystem, provides additional value to everyone. And I'm really proud to already have 24 members now in QBN. So what we are doing, we focus definitely on people behind the innovation, because people making business, not the organizations. And we promote networking, collaboration. We provide startup support, marketing support, and so on. So if you would like to connect to potential business partners or project partners, gain insights into organizations and markets, get fast access to private and public funding, or just drive the agenda and have a registration priority at all of our events, and many more, you're welcome to join our growing network. And one of our key activities at QBN as a network are our working groups, the so-called QBN meetings, for the different subfields of quantum technologies, means sensing, imaging, metrology, software and simulation, communication, computing, and the enabling technologies like photonics. These QBN meetings are a kind of virtual replacement at the moment, hopefully in the future physical meetings. They are interactive meetings with valuable market insights, business networking opportunities, and our members actively define our focus. So the content and agenda and so on is developed together with our members. And the focus is on what each participant can do for the others and what the others can do for the individual. So the objectives are always to identify and discuss relevant challenges and trends in R&D and business, and to initiate, of course, collaboration and joint projects. So therefore, I want to highlight one of the upcoming events, which is the QBN meeting on quantum sensing with a focus on diamond quantum sensing in 2 weeks, which is supported by Qnami and Element 6. And we have a very, very good agenda with brilliant speakers like Fedor Jelecko, for example, and Roger Fu from Harvard University, and so on. So please don't hesitate to register for this QBN meeting. Yeah, with this, I want to end my short presentation about QBN. If you're interested in job openings, news from the QBN members, upcoming events, and so on, just follow us on LinkedIn and Twitter. And if you like this video and want to see more, you can subscribe to our YouTube channel and yeah, follow us there to receive the latest about our European Quantum Leadership sessions and QBN webinars. With this, I want to hand over to Mathieu Markham, and he will tell us more about the engineering of diamond materials for quantum technologies. So Mathieu, the virtual stage is yours.
Cool. Let me just share my slides. Start. Cool, thank you, Jonas, and thank you very much for giving us the opportunity again to talk at your webinar and give us Element 6 perspective on quantum materials for sensing. Obviously, we're Element 6, and I work at Element 6, and our main work that we do is obviously towards diamond. So this is all going to be about diamond quantum sensing applications. So what I'll go through today is I'll just give you a very brief introduction to diamonds and diamond quantum technologies, along with then going into how we grow our diamonds. And then I basically, the rest of the talks are effectively split into two sections. One, I'll just talk through some of the different types of materials we've been developing to give you a sort of flavor of some of the challenges we've had to overcome, but also give you a flavor of the different materials that you can produce by diamond synthesis. Because it's non-trivial to, there's no button, unfortunately, on our reactors to allow you to push a button and deliver one type of material. You have to do a lot of work into engineering the diamond. And I'll go through that. And then I thought just to give you guys a sense of what you can do with this technology, I'll go through a few different kinds of sensing application case studies. Okay, so onto diamond itself then. So diamond is an extremely interesting material. It's what I call an extreme material because it has some very extreme performance properties. Most of what Element 6 it does at the moment is around the mechanical space. So we all know diamond as being a very hard material. And so obviously a lot of applications where you require hardness, like machining, for example, manufacturing cars, all those kind of things typically use diamond in that application. But diamond does have a lot of other properties beyond the mechanical. I always like the thermal properties. So diamond has the highest thermal conductivity of any bulk material. So it's a brilliant material, say, for example, to use as heat spreaders. And as we move into more and more electronic applications where power densities increase, thermal management is a challenge, and therefore materials like diamond can really help push the envelope and push the performance of materials. But today we're here to talk about quantum, so I'll go on to quantum and why diamond is an interesting material for quantum. So diamond, all of its properties really relate to the lattice properties. So the fact that it is very rigid lattice, so all the bonds, sp3 bonding, so very strong bonds with very light atoms, and you have this symmetry where all the atoms are equivalent, all the bonds are equivalent. And that leads to all of diamond's interesting properties, but specifically for quantum technologies, what it really means is you have a very high Debye temperature, which essentially means you've got phonons in the material, but they don't generally interact with electronic spins associated with defects, which leads to this ability to make a material that has high sensitivity for magnetic sensing applications, room temperature operation, and a very consistent behavior. So most of diamond quantum technologies is based around the nitrogen vacancy defect. There are other defects out there that people are working on for different applications. However, I think the NV is probably the main workhorse because of its very interesting properties. So specifically, the nitrogen vacancy defect in diamond consists of nitrogen replacing one of the carbon atoms, and next to that is a gap in the lattice or vacancy, and specifically it's the negative charge state that we use, and it has this very interesting energy level structure such that when you illuminate the NV defect with green light, and that can be laser light or LED, green LED, if it's in this ground state, you get this excitation to the excited state, and then it drops down back into the ground state, emitting a red photon. However, if it's in this particular state, in these states here, then you actually go via this intersystem crossing state down here, back into this ground state here. So you've got this very simple energy level structure such that just by pumping it with green light, you can put it all into one single spin state. And then this transition here is a microwave transition, so you can flip that spin state simply by applications of microwaves. The readout process is exactly the same kind of mechanism, where basically the amount of light you get, so you get more light from this state than you do from going around this other route, and therefore you can measure or read out the spin state simply by measuring whether it's a dark state or bright state, allowing you to read out which spin state you're in. And this leads to this thing called optically detected magnetic resonance. You can do it other ways. There are other electronic ways of doing it, but I'm going to concentrate on this today. And so in this plot here, we can see microwave frequency. And as we scan the microwave frequency, when we hit resonance, so when we hit this resonance here, we get a dip in our fluorescence. And as we apply magnetic field, these two energy levels here, which are degenerate at zero field, split according to a Zeeman interaction. And you can obviously, for things like magnetic sensing, you can extract out what the magnetic field is. And I think what's really exciting is you can do all of this at room temperature. So this has led to lots of different applications. Magnetometry, I think, is probably one of the forerunners, but there's other sort of sensing modalities such as temperature sensing or electric field sensing. Obviously, things like quantum computing, quantum communication is also something that there's a lot of active work in this space, and things like making room temperature mazes out of diamond. Obviously, today we're going to talk about sensing, so I'll concentrate on that. From a diamond perspective, what's actually quite good and what is that the materials required for these applications, basically you can split them into three different camps. And it's basically bulk materials where you have uniform NVs throughout the material, NV layered material where you basically have thin layers of NV enriched material on top of what is otherwise low NV material, and material which is high purity diamond where you can use single NV defects. So I'll go through how we make those materials. So we use a process called chemical vapor deposition. We do also have high pressure, high temperature in-house. That's what my colleagues in the abrasive sector use. However, the reason chemical vapor deposition I think is quite key for quantum technologies is you have much better control over the inputs into that process, so that you're able to tune things like the nitrogen concentration in the material, and therefore the NV concentration, as well as things like the isotopic purity of the material. And so in our reactor, we have use a microwave assisted process, which is basically a microwave chamber into which we inject microwaves. The gases we put into that chamber, things like hydrogen and a carbon-containing gas such as methane. Those are obviously the two key ingredients, and then you add things like dopants in there, such as nitrogen, to add into the material. This cartoon here just basically shows the process and the role that hydrogen plays. So hydrogen really plays a key role in this, where firstly it creates the species. So if we look at this methane here, we'll see a hydrogen come along and knock off one of the other hydrogens creating a methyl radical, and it's those methyl radicals that then come in and build your diamond up, and you've kind of got this bricklaying process, if you like, to build your diamond. And therefore you obviously can do it in layers. But there's a lot of factors we need to consider: the conditions, the temperature, the substrate, etc., when producing the material, because there's lots of parameters that go into the diamond which can affect the properties. Which is basically what I have here. The three main properties that we're interested in are the spin lifetime, T2 star, or some applications it might be T2. The diamond geometry and how this affects the performance is obviously its ability to get the light out of the diamond, because you're measuring this red light. Any red light you don't detect obviously is wasted signal, so that's an important consideration. And NV minus emission contrast. So that's basically the emission you're getting from your NV minus defect that you're using. That's an important factor when it comes to improving the performance of devices. A typical device consists of these main components, so like a laser or an LED, which is then focused with some optics onto your diamond NV containing material. You apply an RF source and typically a static magnetic field to split out the various different contributions from the different orientations of the NV defect, have some filter and some detector. And I think that's one of, again, the nice things about diamonds quantum technology is the fact that all these things are relatively standard, relatively easy things that you can already purchase. You haven't got to reinvent new detectors or lasers to make these things work well. So when it comes to probably one of the most important parameters, which is T2 star, there are lots of contributing factors that affect T2 star. So obviously any residual nitrogen in the material can affect or have dipole coupling to the NV defects and therefore affect the spin lifetime. Obviously the NVs itself, a higher density you go, the more self-interaction you can get. NV0, that can also have an effect. You can also get other defects, parasitic defects, which I'm denoting X here, which can have an effect on the spin lifetime. The isotopes, so carbon-13 in natural abundance diamond is 1.1%, and that actually has a significant impact on the spin lifetime. And one that I'm probably going to give a bit more detail on later is strain in the material. So strain basically will act as shifting the ODML line position and therefore lead to inhomogeneous line broadening. So all these are important factors to consider. This plot here is basically a plot of spin lifetime versus the nitrogen content, and basically the assumption is no other parameters are affecting the spin lifetime. So this is the kind of what you'd expect for the spin lifetime, depending on whether it's natural abundance material or carbon-13 depleted material. So moving on to our first case study in diamond materials, which is our 16 ppm diamond we've been developing. So generally speaking, when you grow diamond via CVD, you're growing material which is effectively in a non-diamond stable regime. Diamond is at the room temperature pressures. Carbon really wants to be graphite, not diamond. And so therefore, you can, if you don't control the properties right, you can add in a lot of parasitic defects. So we did a small study where we grew relatively thin layers, about 100 microns of high-end material on low-end CVD substrates, such that we could do short loop experiments to allow us to understand what are the key parameters in affecting the nitrogen and also these parasitic defects. And the parasitic defects, things like vacancy clusters or NVH, typically produce this brown coloration, basic brown color centers effectively, which cause this darkening of the material. And what we can see in this plot here is as we increase our nitrogen, we're actually able to reduce the, as we change our conditions, we're able to reduce the amount of these brown defects, as well as increasing our nitrogen content in the material, which is exactly what we want to do. We want a high nitrogen material, but with a low concentration of parasitic defects. So we were targeting something around 16 ppm. So we did a further study, where a more detailed study of these higher nitrogen content, where we took 3 different recipes measuring both the neutral and the positive charge state of the nitrogen. And that's quite key, because the positive charge state basically means the electron from the nitrogen has gone to some other defect, or may have gone to some other defect which isn't the NV defect. And so therefore you want to reduce the amount of NS plus as much as possible. And we can see that in this, both in this plot and this table here, where by changing the conditions, we're able to increase the amount of neutral nitrogen and also increase the amount of nitrogen. We then selected this particular recipe here because this was a target recipe for our application, and we're able to demonstrate that we can grow consistent material across a whole batch of samples. So we have this very good control of nitrogen. Obviously, you need NV defects. So how do you produce that? We produce that via electron irradiation. So we use electron irradiation because it generates it's a very nice way of generating spin defects or NV defects in diamond without generating too many other defects. So initially we mapped out the irradiation dose versus the amount of GR1, which is the neutral vacancy in witness samples. We then applied that to our diamond, and this is a plot just showing you the irradiation number of runs over a 12-month period, showing again we have consistent control. So we've got this nice material with consistent nitrogen, and then a nice process where we can irradiate it. We apply that to the diamonds, and we can see here a plot of multiple samples showing consistent NV concentrations with a less than 4% variations. So we have this very nice material. Obviously, the key thing is what is the spin properties of this material. And so I mentioned earlier that strain is probably one of the key parameters, and we can see this in this plot here. So this is a birefringence image of the sample, and the coloration obviously denotes a variation in that birefringence. Birefringence typically in diamond comes from dislocations in the material. So if this here in this particular sample, probably a dislocation bundle from the substrate, generating this high strain in the material. And what we can see in this plot here, so this is data from Ron Walsworth's group at Maryland. So this little red window here corresponds to this plot here, and we can see that across that plot, the T2 star varies from 0.36 microseconds to 0.89 microseconds. So large variation across a small area, whereas if we take an area where the birefringence is more uniform, we see that the T2 star does not vary. So the impact on birefringence of greater than 10 to the minus, the impact in this material, if the birefringence is greater than 10 to the minus 5, we get this variation in T2 star. And that, as I said earlier, comes from this parameter here. We can do a little bit further, and this again is some more data from Ron Walsworth's group, where we took a bunch of samples. So this is 6 samples where we measured the birefringence of this 16 ppm material, and then they were able to do strain mapping. So it's effectively looking at the line positions of the ODM line positions across the entire sample. So this is a 500 micron bar here. So these are 3 by 3 millimeter samples, and they were able to then map out this strain and plot this up, and showed that we have sort of less than 25 kilohertz line width variation, which basically, it's in this plot here, means that on that plot I showed you earlier, we are at the limit as to where you'd expect to be for the spin lifetime. And the samples you get are these nice purple color. So these ones, the T2 star of carbon-12 enriched ones are around a microsecond. We can also do this for natural abundance, and this is again a batch of samples where we've shown that we can have this consistent control around about 500 nanoseconds across a batch of material. And if you want to know more about this, please look it up in this paper here. I'm not going to talk about this in too much detail, but we can also apply this process to producing thin layers, and I'll talk a little bit why that's useful later. But basically, you then end up with a process where you have this 16 ppm process on what is a high purity material. So we take a high purity substrate, grow this layer on top, irradiate it, and then have this diamond that can be used for wide field imaging. I'll talk a little bit about that later with some case studies. So I'll go on to just talk about two other materials in different regimes. So I talked about this 16 ppm material, but depending on how you're putting a device together for quantum technologies, you might require different nitrogen concentrations depending on the design or the architecture of the system. So another material we developed, which is the 1 ppm process. This is part of what we've launched as a commercial material called the DNV series. I'm not going to go through it in detail, but I'll just show you the data, which is basically, again, show this consistent nitrogen concentration across a batch, consistent NV concentration, using the same methodologies that I talked to you about earlier. Again, birefringence and strain. Actually, birefringence is probably more key in this material because obviously as we've reduced the nitrogen content, the dipole coupling from the residual nitrogens means that factors like strain are more important. So this material typically has a birefringence of less than 10 to the minus 5, which corresponds to an homogeneity, a strain homogeneity of less than 25 kilohertz. So again, measurements from Ron Walsworth's group. So this is, as I said, as a material that we launched last year, and this the T2 stars of this material were gained around about a microsecond. So moving on to a very different regime, and this is sort of the regime where Mathieu, after me, will be talking about sensing using single defects. And so this is where you need a much higher purity material, so much lower concentration of nitrogen. And so this is a product that's been around a while now, but I'll just briefly talk about it, which is our electronic grade diamond, which basically consists of less than 1 part per billion of nitrogen, and that corresponds to a much lower concentration of NV in this material, leading to these are confocal images from Fedor Yeletsko's group, where you can see the orange dots here are single NV defects in the material. And this material allows you to have T2s up to sort of 700 microseconds. You can also do isotopically controlled versions of this. This is not yet a commercial material, but that obviously has a massive extension on the spin lifetime that you can achieve. And we've recently launched a mil thickness variant. We've now got a 50 micron variant. And again, what I was talking about earlier, you know, the shape of the diamond is obviously important in terms of how you then process that into the final devices. So hopefully this is enabling some new application areas. So that's sort of the end of the bit. We're going to talk about different types of diamond. I'll now go on to just highlight a few examples where our diamond is being used for different application areas. So the first one I want to cover is denied GPS. So this application is based on the fact that the Earth's crustal magnetic field varies depending on where you are on the Earth. So this plot here just shows you the variation. And so therefore, magnetic field variation or the ability to measure the magnetic field allows you to work out where you are on the Earth's surface. And compared to, say, a satellite-based system, it can't be spoofed or jammed in the same way. So we've been working with Lockheed Martin over the past few years, and they've developed a fully mobile magnetometer which takes advantage of this effect, where they can basically produce a low swap system. So this is an image of their system. So it's a 4 kilogram system that uses 5 watts of power, and it's basically designed to withstand high shock and vibration environments. And the big advantage of diamond in this is the fact that you have a vector system. So the fact that the NV defect has a particular crystallographic orientation means that you have specific, you're able to get a true vector signal compared to other technologies. And they're currently trialing the system to use it as a denied GPS system. So moving on to a very different type of application area, and this is something that's been going on in the geological community for a few years now, and I think is building up due to some of the work that Roger Fu at Harvard has been doing. And this is using diamond in a different imaging modality. So the previous one was all about using ensemble defects. And I talked earlier about using generating these layers of NV defects in diamond. And the advantage of that is what you can then do is use a CCD system to then map the position on the diamond against obviously the position of your sample. So you're able to then spatially map out the magnetic field of a particular sample that you might be interested in. And obviously in this particular application, the sort of the trade-off you've got is the thickness of that layer that determines the NV concentration, but obviously it also determines the resolution. So the thicker the layer, the lower the resolution, but the higher the sensitivity. So you've got this sort of trade-offs, trade space that you've got to work with. And what's very interesting about wide field magnetic imaging systems for geology is you're able to measure the residual magnetic fields in geological specimens. And so this was some of the first work that Roger and was also when he was in Ron Woolsworth's group did, which was to measure the solar nebula magnetic field. So this is basically the magnetic field that existed when the solar system was being formed. And the reason that diamond was sort of key to this was the fact that it had much higher sensitivity, but also this higher spatial resolution that you can get compared to other technologies. So typically in the geospace, they've used a lot of things like scanning squid magnetometers, for example, but they just don't have the resolution. And the reason that how they're able to do this, they're able to find the meteorite, and from that meteorite, just because of the geology of the meteorite, they were able to ascertain that that meteorite had not undergone any annealing as it had gone through the Earth's atmosphere. And they were then able to then measure the residual magnetization in that meteorite, and from that they and the sort of this high spatial resolution mapping you can get with diamond, we're able to map out the magnetic field and therefore extract what the nebula field was at the time of the solar system's formation. And there's lots of other applications where geologists are really interested in this. And this wide field imaging technique is also used in sort of other applications, such as biological applications and things like measuring magnetic fields from semiconductor chips. So 2 more case studies to quickly go through. One is on geosurveying. So geosurveying, typically companies, so De Beers already do this. They use squids for tensor to find new mining sites. In this, how they do this is they attach a boom to a helicopter. On the end of the boom, there is your magnetic field sensor. Obviously, in the use of squid, this is actually quite problematic in the sense it's a very bulky technology. It uses cryogenics, and typically mining is not in the most accessible places, so getting cryogenics to them is not easy. And also you have to fly this thing sort of 10 to 30 meters above the ground. So, you know, trying to fly a helicopter with a boom on it, making it slightly more unstable, is not the easiest things to do. So having better magnetic field sensors will potentially allow you to do this sort of geosurveying in very different ways. So this is something SB Quantum, who we're working with, are doing. So they're developing diamond magnetic field magnetometers for tensor gradiometry. And the idea here is you've got, as I mentioned earlier in the other case study, this ability to do vector sensing, which then allows you to give a directionality to your system. And because you also can use multiple sensors, you can build up do a tensor gradiometer, which then allows you to also estimate the volumes of material as well as the position. And the real advantage of this really is you're starting to, similar to the GPS, when you can start to build these things in small systems, which allow you to, say, put them on drones and things like that, which allows you to start doing this exploration in very different ways. So my last case study is on a different type of sensing. So I've talked about magnetic field sensing. This is RF sensing. So this is something that Thierry Debrochet's team at Thales are doing. And this is a project we've been involved with them, with Thierry as part of our European project called Asterix. effectively, you can think of it like a reverse of a magnetometer. So in this process, you you take your diamond and you apply a magnetic field gradient across that diamond, and then obviously the resonance line changes because of the magnetic field change, and that then allows you to then measure the RF field from that system. And you can see that in this plot here. So this is just basically a plot of microwave field, and you can see that this linear sensor sensitivity to the microwave field. The dark line is basically the dip in the ODMR. And the big advantage of this is now you actually have a broadband room temperature instantaneous RF sensor. So you're not having to scan your RF, scan your detection. You can measure all wavelength, all frequencies simultaneously. So that basically brings me to the end of my talk. So I'd just like to summarize with the different materials that I've talked about today. I mentioned the two that are commercially available, the electronic grade diamond and the DNV B1, and these are the properties. But obviously we are doing a lot of work in R&D to develop new grades of diamonds to help facilitate the development of these quantum sensing applications. So I'd just like to then finish off saying that, hopefully I've shown you that CVD diamond is a very powerful and unique material for quantum technologies, with this ability to have this long spin decoherence times, even at room temperature, which makes it, a much more usable system compared to other quantum technologies. But you can also integrate that with relatively easy optical measurement process to measure the quantum state. We've obviously been developing a range of different materials to enable these technologies, and we now have our sort of first commercial products as part of the DNV series, and hopefully there'll be some more products coming out in the near future, or there will be some more products coming out in the near future. So thank you very much for listening. If you've got any questions, those are my details. Please reach out to me either by email or LinkedIn. And of course, I have to thank all the people that do the characterization work. So I mentioned the University of Maryland several times, but also University of Stuttgart also have done a lot of characterization work on our material. And also the people that pay the bills, which is at the moment the EU. So I've got 3 projects, Metabolics, QA, and Asterix. So I will now stop sharing and take any questions.
Yeah, thank you very much, Mathieu. So from my point of view, diamond is definitely such a great material also for quantum technologies, but not only for quantum technologies. So if there are any questions from the participants, please do not hesitate to put them in the Q&A box.
Okay, so come up in the Q&A box. Do you mean to read it out and I'll...
So the first one, do you have studied the effect of the different stress components on the NV properties, especially the dislocation density?
Yeah, it's a very good question. I mean, there's several reasons actually sometimes why you indeed want to add stress into the material to engineer the diamond so you can basically move lines around and affect the properties. Now, generally speaking, for the sensing applications, you don't want any stress. You want to actually remove that as much as possible, which is kind of what I was alluding to. It's actually slightly more complicated than what I described in my slides. It isn't just selecting the lowest dislocation plates. There's a lot of work in terms of choosing the right recipes and changing the recipe parameters, because that can have a major effect on the stress you get in the material. So at the moment, for the processes that I think I showed, we're not limited by strain at the moment. I think if you go to perhaps lower concentrations, there definitely is variation. For example, if you take a single NV defect within electronic grade diamond, there will be some variation in the spin coherence time. You're going to get some distribution, and that will likely all be due to inherent strain in the material.
Okay, yeah, thank you very much. There's also one question. from the registration form submitted during the registration. Are there some use cases in the healthcare or life science sector, and what is their TRL?
Very good question. I should have put some more healthcare applications in my talk. So, I think there's a few different applications. So one of them is similar to the wide field technique that I showed you, looking at the rock specimens. Is a company called QDTI who've been working with to develop these wide field sensors, and what they're doing is looking at an area for proteomics. So they're developing a system where you basically magnetically tag proteins, and then using the diamond, you're then able to measure the magnetic field from those tags, and therefore able to detect low levels of protein concentrations. And proteins are very important in the healthcare sector, because I mean, it's kind of the next stage, if you like, the next revolution, I think, in healthcare, because proteins really tell you what's going on inside your body. So actually having an ability to measure those proteins is key. There is already obviously technology already out there for that kind of thing, but what the QDTI team are building is a system that allows you to analyze things much more quickly in real time without the sort of complexities of some of the other systems.
Okay, yeah, thank you very much. Then I have one last question for you from my side. So as we are here from a network, I want to ask you, what does a good partnership look like for you from your point of view?
So for me, I think for those that hopefully know me, feel that I'm a relatively open individual. I think collaboration is the key to solving these problems. So I think having an open, honest relationship with your partners is a very key thing to do.
Okay, yeah, thank you very much. So I know you have to go for a rescue. Thank you very much, Mathieu, for your talk. And yeah, then we will go directly to the next presentation by Mathieu Munsch. He will talk about quantum sensing from lab to market, the Proteomic Scanning NV Microscope. So Mathieu, the stage is yours.
Thank you, Johannes. And thank you everyone who's showed up. It's really a great pleasure to be here again and have the chance to use this platform and network to share some of our results. So what I'm going to talk about today is how our technology can support development of new computing technologies. And I'll tell a bit the story of our product, how this quantum microscope has emerged. Can you read the slides? Is that all right?
We can see it. Yeah.
Okay, good. Before I start, just a couple of words about Qnami. So we're still rather young startup. We were founded in November 2017, so a little less than 4 years ago. We're based in Basel, in Switzerland, really at this crossroads between Switzerland, France, Germany, at the bottom of what I like to call the Diamond Quantum Valley, which is extending from all the way to Stuttgart down to Basel, where a lot of the history of quantum sensing and pioneer developments have happened. In fact, we have opened recently new offices in Stuttgart. There will be more news around this in the coming month, probably around the fall. We're a team of 15 people. You can see a lot of scientific background. This is absolutely required to pull out a product like the one I'm going to show. You need experience ranging from quantum materials to electronics to quantum control and software. And by now the team has also been rounded up by some more business and executive experience. So I think we're geared up for really neat operations here. We've just closed the Series A, so all in all, this now represents around 8 million investments since the beginning of our story, and I'll tell you how we use this investment and for who. I'd like to start with, this huge opportunity which is coming out right now with our ability to manipulate, store, share, control massive amounts of data. This is really changing our society in very profound ways. It has started already a decade ago, and we only anticipate more across a range of sectors, you know, from communications to healthcare, really a range of sectors. Now, the flip side of this massive surge of data is that it takes a toll on the environment. Just to give one number, it's expected that by 2030, 20% of the world's consumption of electricity will be dedicated to ICT, so technologies around information and communication. This is the equivalent of 1,000 nuclear power plants running 24/7. And a third of that is used in data centers for data storage. And you know that this is storing data, but also essentially dissipating that energy into heat. So there's really a question today on how we can combine this high level of performance, but also reduce the energy footprint. And this is even more important because we also come to that point where the technology that has been available for the past 50 years based on silicon and Moore's law is slowly nearing an end, so we need new strategies to improve further. The good news is that there are solutions out there which can solve this problem, and I want to highlight two of them. One of them is called Spintronics. Both of them are highlighted by the International Roadmap for Semiconductors, by the way. So Spintronics is one of them. It's probably best exemplified by a new type of magnetic memory called MRAM, which I'm sure some of you have heard of, which offers the promise of better storage. It's a non-volatile memory, which improves the current state of the art, but also can massively reduce the energy consumption. And on the other side of computing and processing, here I'm sure everyone knows about the quantum computer and this promise of huge computational power for just a fraction of the energy bill. So those technologies are emerging. There's been massive investment, for example, in a quantum computer. There's an involvement of all the major industrial players in the semiconductor industry for the Spintronics and the MRAM, but still quality control tools and characterization tools are missing to fully leap from the lab or the production design phase to a fully scaled industry. This is exactly where quantum microscopy, quantum metrology can kick in, and our product in particular. So here you have a picture of the Proteus Q, which is the first quantum microscope that we have developed here in Qnami over the past 2 years. And what this guy does is that it allows scientists and R&D engineers in their research lab to look at these types of new electronic design chips and materials and understand them better. It offers higher sensitivity, extremely high spatial resolution, and all of that in a fairly intuitive way without the need for understanding quantum. This is the result of a combination of many different technologies. For the experts in the room, you have the quantum sensing part. I'm going to dwell a bit in a second. You have atomic force microscopy, you have confocal optics, and you have radio frequency, all of that combined in that tabletop instrumentation. So this is for now used by mostly scientists in academia and large research technology organization, but is also interesting for industries. And what it does for them, it allows to look into their chip designs and actually try and control and improve the error rate, which is the big problem both for quantum computing and MRAM if you want to improve either the architecture and scale up the number of bits you use, or simply improve your yield and you want to fabricate with better consistency. So with these type of tools, our goal is to support this industry in reducing their error rate, obtain reproducible audit trails, and eventually increase their manufacturing yields. And that will allow them to really go from niche markets where they are now with an application which is a value proposition which is really valid, but only limited to a certain niche application, to a really full-scale mass market impact. So really the key of our technology is that we use these quantum sensors, and you probably all know here the Schrödinger cat, which is this kind of system which is quantum as long as it's in this box, so it's in this superposition of states. The problem is that as soon as you open the box, the cat is either dead or alive. It can't be both. So this is the complexity with quantum systems. If you let them interact with the environment, they start to lose their quantum properties. And when you build a quantum computer, you've probably seen how they look. Everything is done so that they don't interact with the environment. They're shielded from any field from the outside. They're cooled down. They're put in vacuum, etc. What we do is we use exactly this same property and this strong interaction with the environment as a good property, because it turns out that this is what it means. It's an excellent sensor. The only thing that you have to do is to be able to control that system and put it back into a quantum state as often as possible, or as often as needed. So we use diamond technology, and I'm really glad that Matt introduced that in so many details, because I can then remain on a fairly high level picture. We use these NV centers in diamond. The reason is that they are quantum systems that work at room temperature. It's a key property when you want to do metrology or support an industry which operates at room temperature. And they have then three other main advantages, which I'm highlighting here. Because of the atomic size of this sensor, we can provide ultimate spatial resolution. You cannot think of a smaller sensor, so we can provide the best resolution that is achievable in nature. The second property is that because this atom has a quantum behavior, we can use this quantum system to get a boost in sensitivity compared to other classical solutions. And the last advantage is that because it's a quantum system and its behavior only relies on simple fundamental constants, its behavior is exactly the same as the next quantum sensor. So this provides extremely reliable analytics. The results of a measurement is not going to depend on the sensor, but only on the environment. And if you go for another sensor, you will get the same results. So this reproducibility is absolutely key, in particular for the industry environment. Now, putting such a sensor and making it small and approaching it to the sample is not easy. And this is one of the core innovation at Qnami. It's what we call the quantilever. So this is really the sensor. And to give you a scale here, that's an image which is taken with an electron micrograph. The gold part on the top left is smaller than a hair. So really, this is really small. And then what you have in pink is all made of diamond. And you have this very small tip. And at the very end of that tip, we have introduced one single atomic defect that we use as our sensor. And by scanning that sensor across a material of interest, across a sample of interest, or a chip of interest, we can map out properties like magnetic field or currents from this sample. The other good thing is that this is now a process which is scalable. We use synthetic diamond, no need to go to the mine, and Mathieu has explained how they produce that. So we start from this material, and then using techniques which are inspired by the silicon industry, lithography, dry etching, we can produce these type of sensors at scale. This is what you see on the right side. It's a top view where you see many of those sensors before they're being picked individually. And then through a careful individual quality control process, we can ensure robust and reproducible quantum properties for everything which is shipped out from here. Now, when we want to build a full-fledged solution, a quantum microscope, there is a number of challenges. We've just talked about the sensor solution, but also we needed to think on the system as a whole. As Johannes kind of introduced in the beginning of the webinar, it all started on a gigantic optical table, probably 2 square meters with lots of optics everywhere. This is, of course, not a solution for users that are not experts. So really a key part of our developments over the past 2 years was to find this right platform and adapt it so that we have a robust, customer-driven instrument that will answer their needs. So we are meeting a certain customer usage, and it's not anymore the same as the one for making a proof of principle. So we really had to adapt the technology from the proof of concept to a place where it can really serve the needs of our customers. And this we've done pretty successfully together with our partner Oriba. Oriba is a $2 billion company and a well-established manufacturer of scientific instruments. And last but not least is the software interface, because if you eventually want to benefit from the quantum boost, you really need to be able to understand and transform this information into data that means something for the end user, and you don't want to leave that to the end user to have to understand all the quantum mechanics and how the environment and the sample might affect the sensor. So this is ongoing effort. I'd say this is continuous effort, so that because we have every day new use cases, so that we can provide a solution that really provides to our users data and not just raw information. This is a quick overview of the sample. I'm highlighting here 3 different imaging modes, which kind of allow to go from very fast scan. This is what you have on the left, where you kind of already kind of get a feeling of what the sample looked like, what the textures might be, if there is some geometry to be observed, to the very right, where this is now very focused into a specific area of interest. And here you can have a really fully quantitative measurement. So you notice that the scale on this right side of this image is really a value for the properties that you're trying to measure, the magnetic field in this case. And this quantitative assessment allow you to feed your models and maybe calculate retention rates for memories. It is really key information. The product market fit has, I'd say, been demonstrated. At least we have excellent early traction. The product's been launched about a year ago, and we count already 4 really high-profile users. Among them is the group of Nobel Prize winner Albert Third, and also the founder of the whole field of Spintronics. He invented GMR, giant magnetoresistance, which is at the base of any hard disk drive that you might have used in the past. And we also have the Fraunhofer Institute in Germany. This is really showing that it bears interest for the industry. What they want to do is to show that this type of instruments can serve the semiconductor industry and understanding their design better. So they're developing an application lab for themselves where they can propose and offer that type of technology. For the scientists in the room, I just wanted to flash a few examples of what our users are doing with this technology. It's a wide range of research. Maybe I can highlight the top left. This is a new type of memory based on some chromium oxide antiferromagnets. So what these research group allowed or managed to do was a first fully electrically controlled memory based on this new material. It offers lots of interesting perspective for the industry. I can talk an hour about it, or just a minute if you have questions later. But really where our technology was essential for them was they needed to map the property, the behavior of these materials so that they understand how bits 0 and bits 1 are encoded and how robust that is. And you have a range of different applications. Maybe some of you know skyrmions or antiferromagnets or van der Waals, these 2D layers, which are becoming extremely popular now in research, but also in the industry, actually. The flagship example being graphene. And one slide here to really show why the instrument is unique. This is another piece of research where they look at the same material that I've just talked and looked at different temperatures, and it went from a region where there was no specific pattern to be observed to a region where you can really see some magnetic field pointing up, down. And this was a key finding for them. And what I want to highlight for you is the scale. We're talking here micro Tesla. So this is an extremely small magnetic field, which you could not measure with any other technology in the past. And the other thing which I want to highlight is the scale. We're talking here 500 nanometers, so that you can see that the structures are actually 100 nanometers, sometimes even smaller than that. And any other technology would also not be able to see the difference between these blue and red regions. So really, for those two reasons, quantum metrology and NV centers in Diamond offer a complete new avenue for these researchers. All right, and now this will be my almost final slide, connecting back to this bigger challenge that I mentioned in the beginning. How do we help more specifically to address those? Well, for quantum computing, as you probably know, you need, at least for some of the technologies available out there using superconducting materials, you need to cool down to very low temperatures. And one of the problems is that you don't have so many metrology tools at low temperature that functions and deliver the analytics that you need. So one of the activity that we are starting now is to essentially put the Proteus Q in a fridge so that we can offer the same value proposition in this type of environment for this type of industry. And another activity that we're pursuing is demonstrating use cases towards the semiconductor industry. And here we anticipate the development of another instrument where the main difference would be the sample size that we can accommodate. For now, we're talking very small 1 centimeter square samples. But this industry, if you want to think of quality control, maybe even nearline or in the production line, you need to be able to handle sample so-called wafers, which are 300 millimeter, so 30 centimeter wide. So this is a technological challenge, but still an important one, which we're looking into together with partners like IMEC. So to conclude, I would like to mention in this audience that this is really a completely new technology with lots of opportunity ahead of us. We've just closed the Series A, and actually we have some projects that are starting now, and there will be a lot of new open position now and in the future. So I would like to encourage everyone to visit our website, to contact me and discuss our already advertised positions. There will be more in the future. So if you're interested to join the quantum wave and participate into building the future for Qnami, but I'd say more generally the participating to the quantum ecosystem, I'll be more than happy to hear about you. And with this, I'd like to thank all of you and Johannes in particular for organizing this webinar.
Yeah, thank you very much, Mathieu. So I'm looking very much forward to more family members in your Proteus Q family in the future. There's one question for you. What is the current reached limit on measurement precision, and what are perspectives to improve it? Is there a physical limit that will never be overcome, something like shot noise for photons?
Okay, so we will be talking two different resolutions here. One is the resolution in magnetic field, so how small the magnetic field we can measure. And here, I'd say our resolution is a microtesla, and we can improve that with more elaborate quantum protocols down to probably around 10 nanotesla, and then there will be a limit due to the coherence time, this T2 time that Mathieu introduced in the previous talk. And then there is another resolution, which is the spatial resolution, so how small we can see. I mentioned that we have this single electron or a single defect as a sensor. So this is the theoretical limit. Now, when your sensor is so small, it's not the sensor anymore that determines the spatial resolution. It is the distance at which you measure. So for us, the game is to get as close as possible from what we try and measure so that we can improve this resolution. And today we are around 40 nanometer, going to 30, and our expectations is to deliver 10 nanometer in the coming years. Going beyond that is possible, but is taking more challenge. You then have this trade-off between sensitivity, the resolution in field and in magnetic field, and the resolution in spatial topography.
Okay, thanks. Yeah, it's also connected to the next question. What are the requirements for the surface that you want to measure?
So the surface better be rather flat. So when we think, for example, of semiconductor process, where we can contribute is after thin film deposition, or after the first layer of the first processes. When the structure starts to have profile ratios with stuff going up a micron and down a micron, this is not ideal. Because our probe is still pretty large. We have the NV centers close to the end of the tip and close to the sample, but the probe is still very large, so you would need to convolve with this dimension.
Okay, thank you. Yeah, then also the question for you: what would the perfect collaboration partner look like for you, for Qnami?
The perfect partner. So it is certainly someone that looks in the same direction. And I think we start to see a lot of that. And in fact, what I would say is that there is not a perfect partner, but there is a lot of perfect partners. This is what we need most in this industry right now, is to kind of thicken a bit the ecosystem. There is, I would say, the value chain starts to look like solid. There is at least a player at every point in the supply chain. But probably a healthy ecosystem demands more than that. So I'd say that this is where partnership ecosystem needs to be improved.
Yeah, and hopefully we can close the gaps in the value chain with the upcoming calls in Europe and Germany and the other countries.
I think this can only help. Yes, because we see a lot of SMEs and startups contributing to this value chain and supply chain. Yeah.
Okay, yeah, then thanks again, Mathieu, for your nice talk. And yeah, let me introduce you the next speaker, who is Robert Rölver, Senior Project Manager at Q.ANT. And he will give us an industry perspective on diamond quantum sensing.
Yes.
So, Robert,
okay.
welcome.
I try to share my presentation. Can you see it?
Yeah,
already?
We can see PowerPoint.
Okay, then I will start.
Yeah, looks great.
Oh, great. Yeah. Thank you, Johannes, for your kind introduction. Some of you might remember that I was previously within Robert Bosch GmbH in corporate research, and I working on diamond sensing, and I joined the company Q.ANT in February, and I will talk a little bit about my experience, general experience in diamond quantum sensing, and is with a special focus on what Qwant is trying to do in this field. Okay. First, I would like to briefly introduce our company. Qwant is part of the Trumpf Group, has been founded 2018 as an internal startup. Trumpf is a family-driven company, is known for its experience in industrial laser technology, was the first company that that used industrial lasers for metal, for automotive industry, for welding, for example. And this kind of innovation spirit is holding on in this company, as the owner family, the family Leibinger, decided to found this internal startup to explore the possibilities of the business opportunities in quantum technology for the Trumpf company. Yeah, and we think that these 4 technology fields displayed here will benefit from the groundbreaking research done in quantum technology and quantum physics during the past decades, not only in Germany, but also worldwide. And this will be, of course, communication. You know, all the experiments of quantum communication using satellites. So this field is evolving fast. Then vision and imaging under the hashtag quantum imaging or ghost imaging, with the experiments done by Anton Zeilinger in Austria. Then, of course, computation and simulation probably having the highest business potential, but still, I think the biggest challenges among all these technology fields that need to be overcome to generate business. So we are keen to see first real quantum supremacy in this quantum computation, solving a real industrial relevant problem better compared to a classical computer. And then the topic for today is, of course, sensing and measurement, which probably has the highest TRL level among all these. And as we have just seen in the talk by Mathieu, that there are first products on the market based on quantum sensing principles. So we have already talked about this valley of death. So what we have here is the basic researcher on the left, and on the right, the industry. And what the research is doing, they are doing basic research, and some of these basic researchers are also thinking about applications and doing proof of concept experiments, for example, in magnetometry or similar experiments done with diamonds in the past. And there's, of course, a long way to go from this to the right side. And if you look at the different interests of the stakeholders, the academic researcher is performing an hero experiment that can only be driven by an expert, probably with PhD level in a university. The experiment is not so relevant how much it costs, but what this academic researcher would like to see is something really a new effect on new physical principle. And the motivation is to publish it in a high-ranked journal in the end to prove his impact, the impact of his research. Then on the right, we have the industry leader, which is seeking for a scalable production. So it must be something that can be produced in certain quantities with certain quality. Then the product needs, everyone needs to be able to use this product. There should be no special requirements to use this kind of quantum product in our case. The product needs to meet certain cost requirements, of course, and it needs to generate profit. So you need an application which has the potential to gain profit, to become a real mass product in the end, or something that the customer really needs and would like to pay a lot of money for it. And in between, to bridge this gap, we need something that we call enabling technologies, which requires a lot of engineering. So, for example, shown in the first talk by Mathieu, this diamond growth is really an enabling technology, which took about, I think, 10 years for element 6 to go from first CVD nitrogen doped samples to this real high quality diamonds with NV concentration in the ppb range, or with T2 times of a millisecond. And this is exactly the position that Qu.ANT is working on, is to work on these enabling technologies and do the required engineering to get proof of concept experiments to production prototypes. So here are the examples of what you can do with diamond. So what already Mathieu has shown in his talk is this RF sensing performed by Thales. Then we have work on gyroscopes, publications by the group of Dima Butka in Berkeley, which have shown theoretically that it's possible to also use NV centers to build a high quality gyroscope. Then pressure sensors. So as an example of my career, the first patent that Bosch has filed in NV based sensing was a pressure sensor. Then we have all this biosensing stuff, where groundbreaking research is done by the universities of Stuttgart and Ulm, where they have shown single molecule sensitivity and doing nuclear magnetic resonance spectroscopy on single molecules. And then, of course, the topic for today is the magnetometers, where we have really come from these proof of concept experiments to near production type prototypes, like documented in this publication by Bosch, where we also have been involved from Qu.ANT, this integrated magnetometer, where the sensor head is only on the size of a centimeter and the sensitivity already way below or much better than state-of-the-art technologies. And this, I will talk a little bit further now. What this enabling technology development means. Before, just a brief introduction of the working principle already done by in the first talk today. So we have this NV center, nitrogen in the vacancy in the diamond lattice, forming a defect within the band gap of the diamond, having these discrete energy levels, and you can prove the position, the magnetic sensitive position of the energy levels just by shining light onto this defect, and you have a red fluorescence. If you have an additional microwave field, then due to spin conserving, the electrons are excited to the ms plus minus 1 level here on the top of the energy scheme. And then if you apply an additional magnetic field other than 0, then you have this level splitting, and you have two positions in the microwave spectrum here where the light goes off. And the energy splitting, frequency splitting, is proportional to the magnetic field. So what you see here is the ingredients you need: the diamond, then the light excitation, the microwave field, photodetector in the end, and of course then additional ingredients shown on the next slide. And here as a main message, it can be extremely sensitive, which is the main point why people or industry has gained interest into this, because this high sensitivity also offers new chances for new applications and generate business of it. In addition, you can build a vector magnetometer without additional system cost, because the NV Center has 4 different possibilities to arrange within the diamond along the 4 lattice directions. And if you look at the ODMR spectra of such a homogeneously doped diamond, then you have 4 pairs of energy splittings, because the magnetic field projects different onto the 4 different axes. So from every axis you see 1 pair of resonances. So you have these 8 resonances. And from the changing of the resonance frequency of all these, if you observe them simultaneously, you can calculate the magnetic field vector. And for this, you also need, of course, a bias magnetic field that splits, that makes all the 8 resonances visible in your spectrum. Okay, and there's a very interesting publication I would like to draw your attention to, published just recently by Bosch and the University of Mainz, where we have a proof, where it was shown a proof of concept of a diamond magnetometer with a very high bandwidth, where you can observe all these resonances simultaneously. Okay, again, the system layout, you have the light source, the microwave, the bias field, the diamond, of course, probably if you are smart, you buy it from element 6. Then you have the balance detection. To detect the red fluorescence. Balanced means that some part of the light source is also focused on a second photodiode, and then you can subtract both signals, and the remaining signal doesn't have the noise of the light source. Then you need a differential amplifier, analog to digital converter, and then you have the sensor control, where the signals are calculated, and also you control all these the light source, microwave, and bias field by the central controller. In this case, an FPGA. In the future, probably everything can be integrated into an ASIC. On just one piece of silicon. Then you, of course, that was drawn also by Mathieu, you need a good software that every user can use this kind of device. So this is also something that no basic researcher would do. That is something that someone from industry that is going to sell this project needs to take over. And this is also something Qwant is doing. And additional, here you see it at the logos. Qwant started within this field of enabling technology in developing the light sources. And we evolved our expertise also in the detectors and also in developing the required software. So we are continuously building up our expertise, and we already have gained some expertise to develop these complex quantum devices of industrial relevance, meeting the requirements by a product that probably can have some business success. So going into a little bit more into details into our one of our expertise is, of course, the light source, as we are owned by a laser company. So as we started within Bosch, where I have been part of the research, we had this first demonstrator. It was already highly miniaturized. You see it here in this picture. And of course, in terms of light source, if you need green light, the first choice would be to use an LED, because it's very cheap. It has low noise, and it is a miniaturized device because it's just a little, very tiny piece of silicon without further optics. Yeah, we built this up, and what is also published in this paper and can be seen is that the contrast of the detectable magnetic resonance is very low. It's only 0.05% in this case. And this is also then resulting in a sensitivity of 3 nanotesla, which at that time was already pretty good, but it's still 1,000 times below the potential limit, as shown in proof of concept experiments with this 1 picotesla per square root hertz. And what we found out during the development is that the magnetic resonance and this contrast does not only depend on the total power of light, but on the excitation density. So if you have a closer look in the literature, you see here this nice this publication where you see here in color plot the sensitivity of the diamond magnetometer depending on the optical power. This S is the saturation density, 1 is 1000 kilowatt per square centimeter, and here the omega R is the microwave power in terms of Rabi frequency. And yeah, you should go into this direction, being 0.01 of 1000 kilowatt per square centimeter, meaning you need 1 kilowatt per square centimeter to build a very good diamond magnetometer. And an LED has unfortunately a natural focus limit, so it's not possible like with a laser source to focus all the light power onto one spot with an LED. So diamond magnetometry with high sensitivity always would require a laser. And what we learn from this, as a side note, is we have thought from an industry perspective to make something very compact and cheap and used in LED, but that we would run into this problem we never have been thinking about before, although we had many experts in the that were involved in this development. So it's hard to build a perfect sensor from scratch, and you really need to do hands-on work in this kind of developments, because you cannot expect to know everything about such a system in advance. So then Bosch partnered with Q.ANT, with our company, to develop a low noise laser source at 520 nanometer wavelength. And this is a picture of this first generation quantum sensing, diamond quantum sensing laser source we developed, optical power of 80 milliwatt with this fiber interface. The light engine, which is inside this box, is a very small footprint and can be miniaturized further. And what we see in this recent publication, joint recent publication of Bosch and Q.ANT, is that the sensitivity increased or improved much to 340 picotesla per square root hertz. Also, a part of this success is the use of the laser, so the ODMR contrast increased to 0.5% in this device. And this proves that our company Q.ANT can provide valuable enabling technology for quantum devices, not only for diamond magnetometers. And to give you an outlook of what's coming and how this technology can improve further. So the light source used in the published diamond magnetometer was this one, our previous generation 1 demonstrator. Here you see a plot of the noise of the laser normalized to the photon shot noise. And you see it's still 10 to 20 times above the photon shot noise limit of the light source. And our most recent test setup, our most recent development, here we all were able to bring down the noise by an additional factor of 10, being now very close to the photon shot noise limit, which is of course the limit for a light source in quantum sensing. And we seek, of course, for further integration, which also will help to reduce the intensity noise even further. And I think we will see much better diamond magnetometers using our quant laser sources in the future. So now in my last slides, I would like to address potential applications. If I refer to the first slide showing the valley of depth, of course, an industry company will take the risk to get over this valley of depth, which requires a lot of money, a lot of investment, a lot of time, and a lot of expertise to come from these proof of concept experiments to real products. You only do this if you have if you have an application in mind or identified an application that really can be a business success. And one of these applications people and companies are having in mind when it comes to ultra high sensitive magnetometers is the brain-machine interface. So how would this work? Here on the right, you see a picture of very sensitive array of magnetometers that are placed around the head of a person. In this case, it's superconductive squid sensors inside a magnetically shielded room, because these sensors only work in shielded rooms at zero field. And people have, so there are now quite some publications out where these kind of experiments are shown. So what you see in this experiment is that people were asked to think about certain movements, in this case, very simple, just closing or opening the hand in the 4 different combinations. So on the left, left hand is closed, right hand is open, and then you record the brain activity in certain brain regions. And what you see, even if you only imagine these movements, you see differences in the brain patterns or in the brain activity patterns. And if you then use, for example, a neural network algorithm that can differentiate between these patterns, you can think of a brain-machine interface where you just imagine, for example, if movement and the device you would like to control does a certain thing depending on your thoughts. And here, diamond magnetometers come into play because diamond magnetometers do not need cryocooling. They work at room temperature. They can work in a normal environment, at Earth magnetic field environment, because this Zeeman shift is highly linear over a large range, and you can get the sensitivity also at high bias fields. The challenge, of course, is that the sensitivities, for example, the Bosch magnetometer demonstrator is at the sensitivity of 300 picotesla per square root hertz. The best experiments currently are in the range of 1 picotesla, so this needs to be improved by an additional factor of 10, which is the main challenge people are working on to get to make a proof of concept of these kinds of applications, which is part of current research in different programs at the moment. But as a recent advance or recent results, here a publication where it's documented that you can already do this kind of brain signal recording with room temperature magnetometers, but in this case, no diamond magnetometers, but vapor cell magnetometers, being also kind of quantum sensor, a little bit different working principle, but having high sensitivity and also working at room temperature. And for the diamond magnetometer development, we can learn a little bit from this. For example, to use this kind of gradiometric sensing. The advantage of having 2 identical magnetometers for this kind of applications is that you can suppress stray fields. You see it here in these curves. This is the noise, the magnetic noise of the environment recorded by one sensor. And if you subtract the 2 signals of the magnetometers having this certain distance, you can suppress the stray field noise by to up to 3 orders of magnitude with this graduometric approach. And what you see also in this experiment with these kind of highly sensitive magnetometers in the graduometric architecture, it was possible to already record brain activity in normal environment. As you see here, you get an audio stimulus by an in-ear speaker, and the brain responds with this kind of brain signal. And of course, regarding the business potential, there are already market studies around that predict that these kind of devices would increase in business potential quite, have a quite high business potential. There's a market prediction of going beyond $1 billion per year with growth rates of up to 19%. So it's probably a very attractive use case where this magnetometer diamond magnetometer research can pay off in the future. And with this, I would like to finish my talk with this overview of what Qwant can offer in quantum sensing, quantum technology development. So from the beginning in our developments, we seek to do industrial relevant engineering. We have a patented core technology in the different fields. We have currently a team of 17 engineers and quantum physicists, and we have a large network within research and industry. And on my final slide, you see here additional examples of our expertise. So we are not working only on laser sources for diamonds, but also on laser sources for rubidium, vapor cell spectroscopy. In terms of quantum optics, we have this lithium niobate waveguide fabrication technique, the detector electronics to do quantum photonic sensors. We are developing on our own, and we have already first product prototypes in particle sensing. And with this, I would like to close my talk and thank you for your attention and mention the funding by the German Ministry of Bildung and Forschung in the projects Quamapolis and Milliquant, and also here an overview of our development partners. Okay, thank you. Any questions?
Yeah, thank you, Robert, for your great talk. There were already a few questions, but you answered them with your last slides. There was a question about how to improve the sensitivity for the brain-machine interface and so on, but I think you mentioned all these in your last slides. There is another question. Do you envision applications integrating diamond-based quantum technologies, quantum accelerators unveiled by quantum brilliance, processing quantum data provided by quantum sensors via quantum networks, for example, research by Delft University?
In the field of quantum computing, is this the question?
I think this is the question, yeah.
In the field of quantum computing, we are getting active, but not using diamonds, more using photonics. Of course, but diamond, of course, is an attractive platform because the long coherence time of the qubits in diamond are an advantage. However, there is a challenge in scaling this NV centers as qubits, as you need very precise positioning of single NV centers in a diamond, where the needed technologies are not development yet. So another topic for for example, companies doing this very hard or very challenging engineering tasks.
Yeah, thank you. There is another question. When do you think are they cheap enough? The sensors are cheap enough for wide use, and what has to be improved for real relevance for industry?
Oh, it has been shown, I think, on one of the. So if you go to the system, there's one topic, of course, the diamond. But there, for example, element 6 has shown the scalability of using CVD processes. Then we are working, of course, the light source laser development is is done from the beginning to reduce the cost, to use technologies that can be cost competitive. Then regarding here the FPGA, this can be at the end an ASIC, just one piece of silicon, but in ASIC development, the development costs are very high. So this, for example, really only pays off if you produce 1 million or this kind of scales. But then if there's a demand of this kind of sensor in the range of 1 million pieces per year, then it can become really cost competitive when there is, for example, also the motivation for industry to develop scalable manufacturing techniques to change, for example, the setup of your fabrication and to develop certain fabrication tools. But it's a hen-and-egg problem. If there's no market, no one would take the money to invest in the fabrication. But if there's no low-cost sensor, probably no one will think of high volume use cases.
Right, that's why we're here, to address this challenge.
Yes.
Yeah. Okay. Yeah. Then thank you again. And for further questions, yeah, you can contact us for an introduction to the speakers or directly the speakers with the contact details from the slides. And yeah, I want to thank the brilliant speakers, Mathieu, and Robert again, for their brilliant talks, and of course the participants. And yeah, to all the participants, leave a thumbs up if you like our webinar, and subscribe to our YouTube channel. Click on the bell to be informed about new upcoming videos. And yeah, I'm looking very much forward to see you at the next QBN meeting on diamond quantum sensing on the 7th of July. And yeah, I have nothing else to say. Just thank you and have a nice day.